My name is Ako Kammonen, and I'm a postdoc in Professor Raoul Tempone's group here at KAUST. The name of my poster is Adaptive Random Fourier Features based on Metropolis sampling. This is a work done together with Jonas Kiesling, Peter Pleschak, Matthias Sandberg, and Anders Sepessi. First, recall the definition of the Fourier transform and the inverse Fourier transform, where we have assumed that both f and f hat are integrable. Then take k IID samples of these omegas from a p, and then you can do a Monte Carlo approximation of the inverse Fourier transform with these frequencies. Then we can call this part here for alpha hat, and we have this expression here. This is a neural network with a trigonometric activation function. So we have these alpha hat weights and we have the omega weights. Since it's a trigonometric activation function, we can call these amplitudes and frequencies. So the expected value of alpha with respect to the frequencies omega is f, and the variance of alpha is this expression, where we can see we have this 1 over k here. Now suppose we are given some data, xy points, pairs, that are IID from an unknown distribution with the PDF rho tilde. We assume that the data is such that there exists an underlying function f that if you add some noise to it, you get the y points if you evaluate f and x points. And we assume that the noise has expected value 0 and a bounded variance. The question is then, how can you approximate f, or how can you reconstruct f from only the data points? The standard way is in machine learning, you can do is to construct the least squares problem. Here, the least squares problem has a Tikhonov parameter here as a regularizer. So this problem is not linear because we are minimizing with respect to both the amplitudes and the frequencies. And here beta is some neural network with, or this neural network with some activation function. So what we can do here, that since the mean is greater than or equal to the minimum, so we have take the expected value with the frequencies here, but then minimize only with respect to the amplitudes, we get this bound here. So the inner problem here, the inner minimization problem here, is called this random feature problem. And when you have the trigonometric activation function is the random Fourier features problem. The next step we do here is that we minimize also with respect to the probability density function of the frequencies. So then what I will talk about in my poster, if you come and meet me, is that first an error bound for this. Then I will talk about the optimal P to sample these frequencies from, and also how we can sample from the optimal P. Okay, so thank you for listening, and please come to my poster and I will talk more about this. Thank you.